Lesson 7.4, logarithmic functions. So you might ask yourself, why would we even want to use logarithms? They're a convenient way to express really large numbers or very small numbers. And you could use them, for example, in chemistry. So we know a bit about exponents. For example, we know that 3 squared is equal to 3 times 3, which is equal to 9. So now imagine we have a base 3 raised to the power of x, and we know that it's equal to 9, but we want to find out what the exponent is. So this is what logarithms are all about, determining the power to get to a value. And they undo the exponential. So 3 raised to the power of x equals 9 is over here on this side in this form. B raised to the power of x equals y. And to the left of that, we can see the logarithmic way to write this. So using the same values, we would write log. Instead of b, the base is 3, so log base 3 of 9 is equal to x. These two say the exact same thing. So let's try log base 2 of 16 equals x. This can be restated as 2 raised to the power of x equals 16. You can see the 16 went to the other side of the equal sign. The x became the exponent, and then here is my base. So we're asking ourselves what times what times what is going to equal 16. How many times do we have to multiply with a factor of 2? And so x is going to be equal to 4. So if we said 2 times 2 times 2 times 2, 4 times 4, that would get me to 16. So x is equal to 4. Now we have log base 6 of 216 equals x. So we could write this as 6 raised to the power of x equals 216. And how many times do we have to multiply 6 by itself to get 216? And that's actually going to be equal to 3. So you can see the base, the exponent, and then on the other side is our 216. So you just have to kind of get used to that pattern. Okay, so now we have log base 100 of 1, and what does that equal? So remember, we can rewrite that as 100 to the power of x equals 1, and we know that x has to be equal to 0, because anything raised to the 0 power is equal to 1. So log base anything of 1 must be equal to 0. And I wrote it actually 2 different ways, one with parentheses and one without, just because the one without seemed to be a little bit confusing. All right, so because I say this is important, I would write this in your notes. Log base any value of 1 is equal to 0. So put this in your notes. All right, now let's try one with a fraction. All right, so here I gave you the answer that log 1/5 of 25 equals -2. So I gave you the answer, -2. But let's imagine we didn't know. So I would write it as 1/5 raised to the power of x equals 25. And we have to ask ourselves, how do we get this to equal 25? So remember, I have the answer as -2. So that means we know if we have a fraction and we have a negative, it's going to be the reciprocal. So let's look. If I did 1/5 raised to the power of -2, that's going to be 1 to the -2, 5 to the -2, 1 over whoops, excuse me, let's do it this way. We'll flip these, so we'll end up with 5 squared equals 1 squared, which is equal to 25. So when we insert our -2, we can get it to equal the 25. So I'm going to ask you to pause the video and try the next two. So you might try 4 times 4, and you get 16, then you include another 4, and then you get another 4, and finally you find out that 4 times 4 times 4 times 4 equals 256. But remember, we have a fraction, so it can't be to the 4th power. It's going to have to be to the -4th. So x is going to be equal to the -4th. For the next one, if you think of in the terms of scientific notation, we have 3 decimal places, and we know fractions and decimals are the same. So it would be 10, and it would have to be to the -3 would be the answer for the last one. When you have a log with no base, as it's written here, it's implied that it's base 10, and that's what your calculator deals with, is the base 10 value. It's implied, just like when we have the square root of a value, we don't necessarily have to write our little index of 2, that the 2 is implied. So same thing. Below we have a natural log, and the base for a natural log is always going to be e, and that's what we worked with in our last lesson. Okay, so for the 2 examples I gave you, notice that we don't have a base value. It just says log 220 and our natural log of 22. So if you go to your calculator and you look on the left-hand side at keys like 6 and 7, just type in log 220 and right beneath it ln 22 and see what values you get, and then we'll compare our answers. All right, so for this first one, you should get approximately equal to 2.342. And for the second one, I got approximately equal to 3.091. And we tend to round to 3 decimal places. Okay, even though I recently said that we can't use our calculators with logs unless it's log base 10, there is a cheat. Just like in video games, there's always going to be some kind of a cheat. So what I did here was, on the left-hand side, I have log with our base 1/2 of 8 and equals x. I rewrote it, and then I said to get fractions into whole numbers, we have to use negatives, and we know that 2 times 2 times 2 would be 8. So in order to do that with a fraction, it has to be -3. And then here I have the reciprocal. So then if we look at the calculator, I typed in log 8 divided by log 1/2, and look at what I got, -3. So there is a cheat you can use on your calculator. So in a previous chapter, when we were asked to write the inverse, we had to switch the places of the x and y. So if you're given something like y equals 6 raised to the power of x, I'm just going to move the y over to the right, just so that it lines up with what we have here. So we're going to put 6 to the power of x equals y. Then we're going to switch the placement of the x and y. So it's really going to be 6 to the power of y equals x. And now we're going to write it as a logarithm. So it's going to be log base 6 of x equals y. Here I have a natural log. The first thing we're going to do is put the y on the side all by itself. And next we're going to go ahead and switch the order or the spots of the x and y. And then remember that for the natural log, our base is going to be e. So keep that in mind. And I'm going to pause this and just fill it in. Okay, so remember our first step was we just switched the order and put the y on the right-hand side. Then I exchanged the position of the x and the y. So now the x is on the side by itself. Then I wrote it in exponential form, and remember our base for natural logs is going to be e, and then we want to isolate y, so we'll just subtract 3 from both sides. So then I'm going to get an answer of e raised to the power of x minus 3 equals y. So really it's y equals e to the x minus 3. Here I have some parent graphs for logarithmic functions, and we're going to concentrate just on the first graph because this video is getting to be long. But notice here we have g of x, and here's my g of x. Here's my line of reflection, y equals x. And the domain is going to be, if you remember, all real numbers. Y is greater than 0. And our asymptote is y equals 0. Now if we look at the reflection, we're going to see that the domain is x is greater than 0. You can see that right here. The range is going to be all real numbers, and the asymptote is going to be x equals 0. So everything kind of switches places. All right, so you might be given something like this. Y equals log base 3 of x. Then we're going to have to change it to graphing form. So first of all, I just rewrote it and put the y on the right-hand side. And then I wrote it using exponents. I made a table of values, and I chose some values for y, 0, 1, 2, -1, and -3. And when I subbed those in, I got 1, 3, 9, 1/3, and then 1 over 27, or 0.037. So I solved for my x values. I put in y values to find out my x. Now I'm going to graph, and you're going to see how the line approaches the y-axis, but it's not going to cross it. All right, so I plotted my points. Now I'll connect it, and you're going to see it gets super close to x equals 0, but it's not going to touch or cross. X equals 0 is the asymptote. And remember, you have to graph it by hand. You can't use your calculator to figure this out.